Welcome to week 4 of dynamic balancing. This topic is a pretty important one because it kind of covers off both. It's applicable to both vibration analysis and dynamic balancing, and both very important when discussing all topics vibration and all topics vibration analysis. So we'll get started here. In addition to frequency, which is like our hertz and our cycles per minute, and then amplitude, which is the displacement, velocity, acceleration. The third final characteristic that we need to describe vibration or imbalance behavior is phase. Okay, so a phase with regards to machinery vibration is often defined as the position of a vibrating part at a given instant with reference to a fixed point or another vibrating part. Another definition of phase is the part of a vibration cycle through which one part or object has moved relative to another part. So the main thing here is that it's a measurement. It's a measurement, and the unit of measurement is degrees. So the concept of phase is often the most confusing one to people that are new to this field, and it's important to remember from a practical standpoint that phase is simply a convenient means of determining the relative motion of two or more parts of the vibrating machine. Okay, and again, the units of this are degrees. One complete cycle of vibration going all the way around is 360 degrees. So we're going to be able to identify where the part is in that 360 degree cycle based on the degree relative to something else. So let's go through and I'll kind of try to explain a few examples of this using our basic time waveform to demonstrate phase. The two weights in this picture here are vibrating at the same amplitude and the same frequency. Okay, same amplitude, same frequency. The amplitude is the distance from here to here, and the frequency is, or the period is, the time from here to here. Okay, so each one of their full wave cycles is taking the same period of time, and each one of these is bouncing the same distance from position of rest to upper and lower limits. Okay, so weight A is at its upper limit of travel, ready to move downwards, while at the same instant weight B is at the lower limit of travel, ready to move upwards. So phase can be used to express this comparison by plotting one cycle of motion of these two weights. It can be seen that the points of peak amplitude are separated by a half cycle, or 180 degrees. So therefore these two weights are vibrating 180 degrees out of phase. Okay, so what that's trying to say is that the time that it takes, this guy's going from here, this will say that this one is A, it's ready to go from here to the bottom, and at the same time that it does that, this weight here B is ready to go from the bottom all the way up to the top. The time that it takes to travel all the way to the bottom and all the way back up to the top is really a 360 degree rotation of the shaft, if this was measuring an imbalance. So if this time it takes to go all the way to the bottom and come back is 360 degrees, one half of that from here to here is a 180 degree rotation. Right? And that these two are completely out of phase. And the best way to describe this example right here, if this is plane A, okay, this is plane A, this is plane B, this would be a coupled imbalance. A couple imbalance, if you remember, was when we had equal weight, just instead of it being static where it would fall to the bottom, we had it 180 opposed to each other with our axis crossing at the center of gravity. Okay. Next, we'll look at one where they're at 90 degrees out of phase. So in this one, weight x is at its upper limit of travel, prepared to move downward, and at the same instant, weight y is already at the neutral position, moving toward the lower limit. So in this case, weight y is leading weight x by 1/4 of a cycle, or 90 degrees. Therefore, these weights are vibrating 90 degrees out of phase. Okay, so this 90, this would be 180, this would be 270, this would be 360. So what it's saying is that the difference between the two, how much they're off, is 1/4 of a rotation. So this x is ready to come down, and this y is just moving upwards here, get on its way up, and so it's 1/4 of a rotation. So this x is coming down, and while y is starting to come up and then come down. So that one looks like the weights are 90 degrees, or the weight distribution is off by 90 degrees between the two planes. The last one that I'll look at is when you have two planes in phase, or another way of saying it is two weights 0 degrees out of phase. Okay, so in phase or 0 degrees out of phase. And in this one, you can see that they're both planes are moving or cycling in the exact same time, and ready to move downwards at the exact same time and move upwards together. And this one would be an example. This would be what we described as static imbalance, where we have one opportunity to fix both of these planes with a single calculation. So for going back to vibration analysis and balancing, and just kind of the two, this concept working for both of them, normally phase measurements are not taken during routine periodic checks or the detection phase of the predictive maintenance program. However, when a developing problem is detected, comparative phase measurements can provide invaluable information as part of the analysis to aid in pinpointing the specific problem. Determining the relative motion of machine components can help greatly to reduce the list of possible causes. And in following parts of the course, various techniques for obtaining these phase measurements, we'll go through all of them. There's lots of examples of practical applications where phase measurement and analysis can actually aid the problem identification, which we'll go through when we're doing like the breakdown of applying some of this theory to vibration analysis. Dynamic balancing, however, is a really important application for this phase measurements, because when the problem is unbalanced, the ability to measure the phase makes it possible to balance the part quickly and easily without some kind of like trial and error kind of techniques. And in many cases, rotating assemblies can be balanced in place, eliminating the need for the costly disassembly. We talked about that a little bit before. So balancing techniques using phase are going to be kind of the core of the dynamic balancing course, but understanding the phase measurements and what they mean will also be really important for our vibration analysis course. So we have we're fortunate at the campus to have multiple types, excuse me, I need my coffee, multiple types of vibration and phase measurement equipment. We have some of the simpler, older style that uses a strobe light, or a stroboscopic light, And then we have some of the newer, fancier equipment that uses lasers and tachometers to measure the phase angle of the vibration. So first one we'll look at is measuring instrument setup for measuring with a strobe light, and this is what we have. So I'm not super familiar with a lot of this kind of equipment because it's kind of been phased out, pun intended. It's not as common anymore because some of the new equipment that you use for this kind of thing has all been replaced with like regular vibration analysis equipment. But that being said, it is important and really handy to understand this. We're going to be doing single plane vector balancing using this type of instrument setup with a strobe light. So what we're looking at here is a vibration pickup or our accelerometer transducer, whatever you want to call it, and it's hooked up to our vibration instrument. And then there's also a strobe light that's hooked up here. And then the important part about this setup is that on the end of the shaft, it's kind of fuzzy here, and you can't really see it terribly well, but on here there is, I'll draw it in a little bit clearer, there is an arrow here that goes on the shaft and kind of points in a general direction. And then on the bearing or the shaft or some other kind of reference point, we have a like a compass that's going to measure the angle. So we have 30, 60, 90, 180, 270, so on and so forth. So how this works is, let's say that there is an imbalance. Let's say that the heavy spot of the shaft is, let's say, right here. So when the shaft is rotating, and it's rotating in this direction, it's going to reach a certain point, and the displacement of the vibration relative to the vibration pickup is going to peak. So the actual, if we were measuring our displacement, our peak displacement right here, okay, before it comes down going the other way, and then there'd be a peak displacement the other way, this vibration pickup is going to sense when we get the peak vibration, and then which means that the heavy spot is right at that kind of closest point rotation. So the heavy spot is actually at the 30 degrees, but because we always don't know where the heavy spot is, and we can't draw an arrow. If we knew where the heavy spot was, and you would just not have to worry about any of this. We don't know where the heavy spot is, and we've arbitrarily drawn an arrow on the end of the shaft. So when this heavy spot gets the vibration pickup, it sends a signal to the strobe light to flicker just once, one time really quickly. And so every time this heavy spot comes around and hits that peak cycle, so if we look at our time waveform, which I'm going to draw it here because my face is probably in the way. So every time it comes and hits the top of the time waveform, the strobe light is going to go pop and illuminate the end of the shaft. So every time it gets here, etc., the strobe light is going to flash. And every time it flashes, because this is turning so quickly, it's turning at 1800 RPM, what the effect that it gives is it looks like the shaft is standing still. And the relative position of the arrow that we marked gives us our phase angle. Now, it's not necessarily giving us a phase angle of where the heavy spot is. It's just giving us a reference to say that the heavy spot is at a phase of relative to the arrow is at in this case 330 degrees, where I've gotten this red arrow pointed. So then what we would do is, if we were looking to calculate the phase of the second bearing or second plane, we would just move the vibration pickup and mount it on the second bearing. And if the strobe light is flashing where the arrow is in the exact same position, then what it means is that the vibration of both planes or both bearings is in phase, or we have a static imbalance. But if we move the vibration pickup or the transducer to the other bearing, and now all of a sudden the bearing is, or the arrow, let's say, is pointing down this way, that means that these two phases are going to be slightly off. They're going to look like this somewhere, because every time the heavy spot is coming around on the other bearing, it's traveling a little bit further around, and making the strobe light go pop, and it's going to be in a different position because it's a different plane. So by taking that same arrow, I drew it in two different colors, but just because I wanted to look at it in two planes, it's just one arrow. So by taking that difference, we can say that this guy here is at, I don't know, let's say 330, and this one here, let's say it's at 200. You could say that these are 130 degrees out of phase. Okay, and when we get into the vector balancing, it'll make a lot more sense when we get into the procedure of why that's important. So anyways, there's also really valuable information that can be found from this with determining or eliminating possibilities of or causes of vibration. Okay, so that's one of like the old school methods of doing this. It's very effective. In order to do this, you have to have kind of access to one half or one side of, or the end of the shaft. You have to be able to see it to put your arrow on it, so that when the strobe light flashes, you can get reference between the two planes and how out of phase they are. If you're not able to do that, what you can do is you can just mark on the shaft two different positions. So if this is like a cross section of the shaft, you would take a marker or a sticker or something that was distinguishable, and then on one side of a shaft maybe you would do an X, and then on the other side you would do like an O or something like that, or you do like an X and a square, or two different markings, so that you can look at it. You can look at it from the side here. And there's my little eyeball. So when you're looking at it from the side, you can see where when the strobe light goes off, you can see whereabouts that X is going to be. It might be up here. It might be down here. But if the phase angle is 180 degrees and you're using that X when the strobe light went off and the X was on this side, you're obviously not going to see it. But if you had drawn a 0 on the other side, that 0 is going to be on this side somewhere over here, right? So you can kind of determine on the shaft how or where the phase angle is relative to the peak displacement picked up by the vibration sensor. The other way to do this, and the more kind of modern way to do this, is with your vibration instrument, a pickup, and a laser tack. So how the laser tack works is, when this machine is running and rotating, so it's going to rotate, let's say, this direction, this laser tack shines a it's got like a little laser pointer that it points at the shaft, and then there's some reflective kind of like it's like this 3M reflective tape, kind of like what's on your Visi vests of your like safety equipment. And so what happens is the laser hits that, and then it bounces off of there and comes back in, and there's a sensor in here that reads it. It doesn't bounce off when it doesn't have that reflective tape. It has to be spot on against that reflective tape. So when the shaft comes around and the tape passes underneath the laser, the reflection comes back, and then it measures that as a position, which would be your phase angle, which would be 0. Okay, so if we're gonna trend this one on a graph, then what it's able to do is, if this is our displacement plane and this is our time, what it's able to do is say, okay, I just picked up a sensor of my laser here, 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 and here. And then what it does is it looks at the vibration reading on the vibration pickup, and let's say the vibration looks something like, oh, this is going to be hard to do, something like this. Let's say something like that. What it's able to do now is, at this bearing, it's able to say, okay, if this is my 0 phase angle, my peak was here, this distance between here and here is, say, 360 degrees. So now this distance between here and here is maybe, I don't know, 280. I'm just making up numbers here. Okay, so what they're saying is that the peak displacement, and it will tell you that it's got like 4 mil displacement at 280 degrees. Then we would take the vibration pickup here and we would move it over to this other bearing. So there'd be like, this shaft would extend out and there'd be another bearing over here that we would mount the vibration pickup on. And then on that one, maybe it's a slightly different, let's do green. So on that one, if we read it, it would look something like this, right? So it would look at it and it would say that this one, the peak from our 0 to our peak was only 80 degrees, for example, right? And it might not be equal amounts. It might just be, it might look like this because it's unequal. So it's like a dynamic imbalance. So it's not as much of a displacement in mils. Maybe that one is only 1.5 mil or something. So that's how these ones work and how they measure phase. Hopefully that makes sense on how that works. We're going to be doing both of these in the shop. You're going to be doing your single plane vector diagram measurement and balancing procedure using the strobe setup, and then we're gonna have you guys take turns and do dynamic balancing on this guy using the laser tack vibration reader, kind of more modern setup too. So yeah, hopefully everything there made sense. I'm gonna quickly make another video. I'm gonna do like a little setup. I got a little rig. I'm gonna do hopefully a little bit more explanation on this whole thing to try and tie all the topics and everything we've covered kind of all back together to make a little bit more sense. So that will be for the yeah, I'll just leave it there.